Hey everybody, meteorologist Aaron Treadway here, and I wanted to talk to you about a topic that I've become very interested in for many reasons, and that's weather radar. So let's just dive on in, and I'll show you some of the different features that I really enjoy as we go through this presentation. Radar stands for radio detection and ranging, and it can be used for lots of different things. So, radar is used in different military actions. Radar is used by police to track how fast cars are going, whether or not they're speeding. Radar and sonar can be used in the oceans, and radar is used by us to track different weather features. So, this is a picture of the radar outside our office. This is me on the first day of my job back in 2003. And here's a peek inside. This is our security camera inside showing the radar spinning. It'll go around a couple times and then tilt up and then scan some more and then continue to tilt up as it looks at the different layers of the atmosphere. And what's it doing is it's sending out pulses like this and hoping that it bounces off of something. And that something could be bats, it could be a cold front, it could be a thunderstorm, or just a rain shower. So let's look at a little bit more in depth how it works. So that pulse that's going out will hit an object and then send information back to the radar, and that information back to the radar is looking at the movement in the position of that target that the energy hit off of. So the radar tracks something called phase shift in the radar pulse after hitting the target. So basically it's looking how that pulse changed shape, position, or form after it hit the target. That change then is figured into the different computer algorithms, and the output is then how heavy the rainfall is, the shape, the size, and the intensity of that target. Fun fact is that weather radars actually spend most of their time listening for these pulses to come back. Because the pulses are so fast, they actually spend in an hour's time only about 7 seconds sending the radar information every hour. The other 59 minutes and 53 seconds, the radar spends listening for it. So it does this by following what we call volume coverage patterns. And again, this is where the radar spins, then tilts up, and then spins some more, and then tilts up again. And it continues to tilt up, and this is one of our biggest volume coverage patterns. And that's just so that it can see various heights in the atmosphere. A couple fun facts. The radar cannot see what's going on right at the ground. As we go back, notice that the first line here is actually tilted up and looking away from the ground. So the radar cannot actually see what's going on at the ground here. Another thing is radars can't see what's going on directly overhead. It doesn't tilt all the way to point straight up. So to see what's going on right over a radar, we actually have to depend on the other radars across the country to see what's going on over our area. Radar data, depending on what volume coverage pattern it's in and depending on whether it's looking at precipitation or something we call clear air, radar data comes every 1 minute to every 15 minutes. So dual polarization is a new feature that's come around in the past about 10 years or so for all National Weather Service radars. The old radars used to only look in the horizontal, and so that let us see one aspect of the shape of that target that it was hitting. But now dual polarization lets us get a good cross-section in both the horizontal and the vertical, and that really helps us paint a 3D picture of what's actually falling from the cloud. So given that we know basically the shape most of the time of raindrops, hailstones, snow, biological targets like bats or birds, debris, and other targets, we can use this information in the horizontal and the vertical now to determine basically what's falling out of a cloud. So it really helps us as meteorologists know when there's large hail falling, whether it's snow or sleet or ice pellets falling from a cloud, and then the intensity of the rainfall coming out of cloud, all thanks to this new dual polarization upgrade in the radar. So that's where we are now with radar. We started with the basics back with the WSR 88D, which is actually the follow-up to the 57 radar. Then we had the dual polarization upgrade, and the future of radar, a whole new radar that's being developed, is this. It's called phased array radar. This was a test radar up at the radar test bed in Norman, Oklahoma, where the Radar Operations Center is. And this radar can actually give us new radar data on a matter of seconds. So remember, right now our radars, even in their fastest mode, fastest volume coverage pattern, can only give us a radar scan at the lowest level about every minute to minute and a half. This can give us data on a matter of seconds, this phased array radar, like it did here in the big El Reno tornado, which is what this is. Unfortunately, this technology is still a ways off. Maybe by the time y'all are adults, and maybe by the time I'm a mature meteorologist later in my career, this will begin to be implemented. But due to budgeting and still testing on the technology, this is still probably 10 plus years off in terms of technology. Here's what a tornado looks like on radar. So this is from the Texas Panhandle from several days ago. On the left, you see reflectivity. This is basically how heavy the rainfall is. Probably the most common thing that you'll see on a TV radar or maybe on your app. The greens and the blues are light rain. The yellows and the oranges are heavier. And the reds and then the purples are the heaviest rain. And you see this kind of hook feature here that's often indicative of a rotating thunderstorm, one of those supercell thunderstorms that we've talked about, and the potential for a tornado. When we look over here at the velocity, this is now looking at the winds. And this again is determined by the movement of the targets from the radar. And as you can see, this green is wind towards the radar, and the reds are wind away from the radar. The radar is kind of up over here in the top right corner. And when you have these reds and these greens right next to each other, especially when they start becoming the yellows and the blues, which are really, really high values, this is indicative of a tornado or a strong tornado on radar. So if you can kind of imagine this, winds going towards the radar, then wrapping around and going away from the radar, and that's how you get that rotation signature right there. So when we see this, we issue the red box, which is the tornado warning there, because it's a good indication of tornadoes. You can also see large hail on radars. One of the things that we look for are the purples showing up in the reflectivity. That often means either very, very heavy rainfall or some hail. The other thing we look for are these spikes coming out of the back of thunderstorms, and those are called three-body scatter spikes. Basically what happens is that radar pulse goes out, finds the thunderstorm, hits the hail, and because the hail is so large and kind of odd shaped, it actually reflects down to the ground, that radar beam, then it goes back up to the cloud and back to the radar. And that extra time it took to get to the ground and then back to the radar is actually seen as extra echoes back behind the thunderstorm. But it shows up on a new dual-pol feature called correlation coefficient as just some kind of dead blue data here. And so what we do is, seeing these spikes with the bluish data and the correlation coefficient, we know that that's one of these three-body scatter spikes, which is very indicative of large hail in the tornado. The bat signal is kind of the cool thing that I'm really interested in at our office. And that's because we have a lot of different bat colonies all across South Central Texas. The biggest is this one right here called Bracken Cave, right by our office actually. Here's New Braunfels here, and here's Bracken Cave. But we've got the Congress Avenue Bridge up in Austin. We've got bridges in San Antonio, and bat colonies even out along the Rio Grande in the Texas Hill Country. But going back to the Bracken Bat Cave here, it's the largest bat colony in the world, and it kind of houses itself in the Bracken Bat Cave, mostly during the summertime, but especially since this winter has been a lot warmer. They've stayed around most of the winter, and what it does is it looks like actually a small thunderstorm when they start coming out of the cave here, and it almost explodes. What that is that's the bats coming out, and they like to circle in a big circular pattern as they gain altitude out to go and hunt for the bugs. And so that's why it shows up as this kind of exploding circle on radar. That's the bats. And it's the bats all across South Central Texas. There's so much more that you can see on weather radar. I mean, I could talk to you for hours about this. This is an animation that you've already seen, just the standard kind of outflow boundary in the thunderstorms. This is actually a vertical cross section now of a thunderstorm showing the actual tilt of the thunderstorm, where the updraft would be the heaviest rainfall down at the surface. This is just a standard squall line here. This is actually smoke from the Bastrop Complex fire, the largest fire, I believe, in Texas history. And the smoke actually was large enough, the particulates there, that it actually was picked up by the radar. This was a record-breaking hailstorm that went across northern San Antonio last April. Produced 4.5-inch hailstones. That's basically baseball to softball size. And this is actually kind of cool. This is the velocity again, the reds and the greens. And this is actually the radar being tilted down towards the Earth. And it's actually reflecting off of I-35. So we have a big interstate here, lots of cars on it. And that's what the highest readings here is actually, it's picking up the speed of the cars. So there's lots of different features that you can see with weather radar, lots more research to do, and lots more information. So if you have any more questions about weather radar, feel free to give me an email, give me a shout, or just do some Googling, because there's a lot of cool resources out there for you to find information about weather radar. Thanks for listening.